Hi everyone. In today's lesson, I'm going to tell you about quadratics in vertex form. So, for this discussion, I'm going to start with the basic parabola, y equals x squared. And I represented it in our three forms here, so I've used the rule of three. I have it written as an equation, I have it represented as a graph, and I also have a small table of values which sort of shows some of the points that I've indicated on the graph here. Okay, so this is our basic parabola, and it's also sometimes called the parent. The parent quadratic, I guess you would say, or parent function. You'll learn more about parent functions in grade 11. So, what can we do with this parent function? Well, we can do a lot of things, as it turns out. And so what we often talk about in terms of going from this parent function to other kinds of functions is we use the language of transformations. And so what I'm going to do is I'm going to talk about 4 different kinds of transformations that can be done on this parent function, and then I'll generalize these transformations in sort of a general form using variables. Okay, so preamble aside, one thing that I can do to a parent function that I can do to this graph, is probably easy to see on the graph, is I can move it left or right. So what I'm going to do here is I'm going to move my parabola, let's say 4 units to the right. So in this case, the vertex will move over here, then the rest of the points on the graph will move each 4 units to the right of where they started. Oh, that one goes there, okay. Something like that. And I can connect these points. There we go. So the blue curve in this one is going to be the transformed graph, or transformed function. And what I can do is, now that I have the graph, I can actually generate the table of values from the graph. So I'm going to do that down here, x and y. And what I'm going to do is I'm going to choose points on the graph starting here, then here, then here, then here, then here, and I'm going to write those points down in my table of values. So it's kind of a little backwards from what we normally do, but just bear with me a second. So the first point is here, and that is 2, 4. Then the next point here is 3, 1. The next point is 4, 0. The next point is 5, 1. And the last point is 6, 4. Oh, that didn't quite fit. Okay. All right. Now, this might seem a little odd, but what I now want to do is I want to represent this table of values as an equation. So again, I'm applying my rule of 3. I have my graph, I have my table of values, and now I'm going to write the equation. And it may not be entirely obvious where I get this from, but I'll see if I can explain it to you in a second. But the equation for this table of values and for this graph is y equals x minus 4 squared. All right, so where does that come from? Well, here's the thing. If I take each of these points in my table, so this 2 for example, and I put it into this equation, and I evaluate I'll just do one here actually, instead of just talking about it. So if I take this 2 and I put y equals x is 2 minus 4 squared, 2 minus 4 is negative 2, so y equals negative 2 quantity squared, which is then 4. Okay, so indeed, I do actually have this point. This point satisfies this this relation. I won't do the rest, but if you do each of the other points in the table, you'll see that each of these points satisfies this relation. Now, that's not really conclusive evidence, but I hope you'll agree that if 5 points from a table are satisfied by a particular relation, then there's a really good chance that that table and relation are the same. So we have the graph, the table, and the relation that all seem to match up. All right, let's try one more. So again, I go back to my parent function, and now what I'm going to do is I'm going to move it up. I'm going to move it up, and just because my scale is a little small here, I'm going to move it up 2 units. So the vertex moves there, and then this guy moves there, and this guy moves over there, and this guy moves there. Sorry. Moving each point up. Each point on the graph, I'm moving it up 2. Okay, so that's fine. I have 5 points, and I'm going to connect those up. Here we go. Oh, that wasn't very good. I'll try again. Oh, that was a little better. Okay, so each point on the parent has moved up 2 units. Okay. So again, if I go into my table of values and I use my graph, I see that when x is negative 2, my y value is 6. And when x is negative 1, my y value is 3. When x is 0, my y value is 2. When x is 1, my y value is 3. And when x is 2, my y value is 6. Okay, so graphically, I hope you were able to see that for each point on the red graph, I move it up 2 units to get to the blue graph. Red graph, up 2 units, blue graph. Red graph, up 2 units, blue graph. And from a table of values, this idea of moving up 2 units means that the y value here is increased by 2. The y value is increased by 2. Okay? So that's basically what's happening there. In terms of my equation, since the whole graph is being moved up by 2, that's really saying the y value equals what I had before, x squared, but now I'm adding 2. I'm moving the whole thing up by 2, and I'm adding 2 to the y values. So arguably, vertical translations where we move it up or down, those are kind of easier to understand, I think, than horizontal translations where it moves right or left. Okay, let's try one more. Again, I'm going back to my parent function here, and now what I'm going to do is I'm going to do a vertical scaling. So vertical scaling means that all of the, whereas in the last one the y values were all increased by the same amount, in this case the y values are going to be multiplied by a particular factor. So in this case, what I'm going to do is I'm going to take each point on my parent and I'm going to double the y value. I'm going to double the y value. So in other words, I'm going to multiply the y value by 2. The x values are going to stay the same, however. So in this case, the y value is 0. So when I double 0, I still get 0. Okay, over here, the y value is 1. When I double that, I get 2. And so this one would be 2 also. And then over here, the y value is 4. And when I double that, I get 8. And I get 8 there and there. Okay, so now I have my 5 points. And now I'm just going to connect those up and do something like that. Alright, again, if I go to my table, This idea of doubling is pretty robust. So again, if my x values are still the same as they were before, but the y values are all going to double. So 4 becomes 8, 1 becomes 2, 0 stays 0, 1 becomes 2, and 4 becomes 8. So that's my table of values. Again, that's just taken from the graph. And so now the equation is going to be, so the parent is y equals x squared, but since the y values are doubling, we have to multiply the old one by 2. So it's a vertical scaling by a factor of 2. Of 2. Vertical scaling by a factor of 2. And really, when I use the word scaling, I want you to think multiplication. Right? Vertical scaling is just multiplying, and the vertical is in there to remind you that what's being multiplied is the y values. It's the y values being multiplied. Okay, let's do one last one. Okay, so again, the parent function. And now what I'm going to do is I'm going to reflect. I'm going to reflect, I'm going to perform a reflection rather, and when I perform a reflection, we're always going to choose the x-axis as our basis for reflection. So imagine that the x-axis is a mirror. Okay, the x-axis is a mirror here, just like that. And so when we reflect in the mirror, it's the y values that are reflected, not the x values. So that means that here our vertex stays the same. This point comes down here, and then its buddy goes there. The next point comes down to here, and its buddy comes down here. The next point, I can just get that on, and like so. Okay, so this is our reflection. Oh, that wasn't drawn very well. Let me do that again. Okay, a little better. A little better. Okay, so now we have a vertical reflection, or really at this point we're just going to call it a reflection. So now, if we draw up the table of values, then our x's, again, reflection doesn't change the x's. X's all stay the same. But the y values are now negative, where before they were positive. So this is -4, -1, 0, -1, -4. Okay, and so the effect, if you look at the y values here versus the y values down here, the effect is just to multiply them by -1. So there's almost, when you talk about reflection, there is a connection to vertical scaling, except in this case we're not making the parabola larger or smaller, right? It's staying the same shape, but what's changing is the direction is changing, right? So it goes from concave up, let's say, to concave down. Okay, so anyhow, our equation then becomes y equals, so the original is x squared, but now since all the y values are negative, we have a negative in front. Okay, so if I put all of that information together, then I can basically relate each of those 4 transformations to a letter. And in fact, 2 of them are represented by the same letter. So if I go in the order that I presented them, H is going to represent a horizontal translation. K is going to represent a vertical translation. And A will represent vertical scaling and a reflection when A is less than 0. So if I take all those things and I write and I put them all together into a general equation, I get y equals a x minus h quantity squared plus k. So if you're the kind of person who likes to write equations down, this is a great one to do. Should go in your notes somewhere. Make sure that you know that one. It'll also be in our classroom. All right. I guess I just want to do a couple examples of how you might use this and how you might, what information you can get from it. All right, so let's do one. So let's say I had an equation, y equals 2 x minus 1 squared, and that's fine. So a typical question might ask you, what are the transformations that are applied to the parent function? And there are two. The first one is there's a vertex. So again, we're looking at this number, and we're looking at this number. So since the number in front is a 2, we have vertical scaling by a factor 2 of 2. Okay, so that's the first thing. And we also have a horizontal translation right 1 unit. Okay, so that's basically that one. One question that you might ask yourself is, well, okay, but where's the vertex? Where's the vertex? And if you think about these transformations happening to the vertex, like the actual point, it's pretty easy to work it out. So you know that originally your vertex is at 0, 0. That's on your parent graph. But if we apply these transformations, and we apply them the way they're written, so in this case, it says we do a vertical scaling by a factor of 2. Vertical scaling means we take our y value and we multiply it by 2. Well, 0 times 2 is still 0. So in this case, we're going to have 0. And then it says horizontal translation right 1. So we're going to move 0, right 1, which will give us 1. So our new vertex is at 1, 0. Now the neat thing is that the once you get used to reading vertex form, you'll be able to pick off the vertex really easily. That's why it's called vertex form, because when you're used to working with it, you can read the vertex right from the equation. One thing that when we start off might be helpful is if you actually write in plus 0 at the end here, because now I think you can see that this 1 turns into this 1, and this 0 gives you this 0. So this h and this k in general give you your vertex, your new vertex. Okay. Let's try one more example. So if I wrote, I'm going to do a little more fancy one, y equals negative 1/3 x plus 2 squared minus 5. Okay, so before I list the transformations, let's think about the vertex. Where is the vertex? I mean, I've got all these numbers here. Some of them are negative, some of them are positive. Really, it doesn't matter. This number is your h. And this number, is blue, is your k. Now, you have to be a little careful with the h here, because this is the way that it's typically written, right, to simplify things. But in actuality, because of the way the general form is written, I should have maybe written y equals negative 1/3 x minus negative 2 squared minus 5. So it's a little bit more complicated, but here I've explicitly stated x minus h. The h is negative 2, not positive 2. Right? If your vertex form equation is going to work properly, or if you're going to read off the vertex easily, then it always has to be x minus h. Right? I hope you can see where that came from. Here I have x plus 2, so I can always turn a positive into a subtraction of a negative. So that's my h. My k is easy though. My k always works. It's the one, it's that one right there. So my vertex in this case is negative 2, negative 5. Okay? If I break this down in terms of the transformations, there are 4 happening here. And I'm going to do them in the order that they're written, right, from front to back. So the first one is a reflection. A reflection in the x-axis. And the second one is a vertical scaling by a factor of a third. Then the next one is we're meant to move left 2. And then the last one is we move down 5. Okay? So one interesting thing that might happen here is we might take one of the points that was on our original graph, on our parent, and ask where does that point go? We've already worked out where the vertex goes, but the vertex is really easy. What if we took the point on our original graph 1, 1? Right? 1, 1 is on the original, is on an untransformed parabola. It's on the parent function. But where does that point go? Well, we have to apply the transformations in the order given, and then that will tell us where this point goes. So if I go, I'm going to walk them through one step at a time. So the first thing I do is I do the reflection. So the reflection means my y value becomes negative. So I'm now at 1, negative 1. Right? That's with the reflection. Okay, I need a little more room here. Sorry. Oop, got away from me. All right, the next thing I'm going to do is I'm going to do my vertical scaling. Vertical scaling. So in this case, again, the x stays the same, but the y value gets multiplied by a third. So I'm now going to be at negative 1/3. Then I move it left 2. So if I move this left 2, this goes to negative 1, and this stays at negative 1/3. And then, gosh, I still need a little more room. Then the last thing I'm going to do is I'm going to move it down 5. So my x stays the same, negative 1, but then I have to subtract 5 from that, so it'll be negative 5 and a third. I'll just write it in mixed form there. So the point where I started, 1, 1, goes through each of these transformations one at a time, and then ends at this point here. And this point on the transform graph is sometimes called the image point. Okay, that's it for today. That's kind of a long lesson. I hope you learned something. I'll see you in class.